Hello, thank you for joining this tutorial today. My name is Arash Vahdat. I'm a senior research scientist with NVIDIA, and I'm going to talk about weakly supervised learning from noisy labels. Many of you know that deep learning is data hungry. Many successful stories of deep learning has been made because of availability of large quantities of annotated data with high quality labels. Sometimes collecting data can be done cheaply, but collecting annotation is very expensive. For example, we may need to train annotators, or we may need to hire experts in a field for annotation. Sometimes we may need to ask multiple annotators to annotate the data to ensure that our labels have high quality. In some problems, we can reduce the annotation costs using some cheap approaches for collecting data or collecting labels. However, these approaches usually come with noisy labels. Label noise is an unavoidable problem because in some problems, because of ambiguity and subjectivity of the annotation task, we may not be able to completely remove the label noise from our annotation process. In fact, many well-known datasets, including CFART and ImageNet, contain some amount of label noise in their training data. So the idea of robust deep learning is to come up with better approaches that can be used for training deep learning models from noisy labeled data. In this work, I'm going to start with a quick tour of prior arts in the area of training deep learning models from noisy labels. Then I will introduce a new probabilistic framework for training deep learning models from noisy labels. And I will show how we can use this for training image labeling models, object segmentation models, as well as object detection. In the last part of the talk, I will talk about contrastive learning and how we can use this new training approach for training deep computer vision models from text as noisy labels. And finally, I will conclude the talk with some open questions in this area. The previous work in this area can be grouped into several categories. The first category is loss correction methods. The basic idea of loss correction is to modify the training loss using some label-dependent noise model. The second category is called robust loss functions. So the methods in this area try to find loss functions that are robust against label noise. In fact, one of the early works in this area showed that both L1 and L2 losses are robust against label noise. The third group is called curriculum learning. The basic idea of the methods in this area is to come up with a weighting mechanism for each training instance, such that the instances that have noisy labels can have less contribution to the training loss. So these methods either remove the contribution of each instance that has noisy labels to the training loss by completely removing it, or by reweighting it such that those instances have low weight or low contribution to the training loss. So the majority of methods in this area try to come up with a weighting mechanism for this task. The fourth group that we will mostly talk about it here is called label correction. So the basic idea of the methods in this area is to come up with a mechanism that allows us to correct some of the noisy labeled instances to have correct labels. The final group is the regularization techniques. So even though the methods in this section are not necessarily designed explicitly for noisy labels, but I wanted to include them here to emphasize that by regularizing the neural networks during training, we can actually ensure that they don't overfit to noisy labels. And this is one of the very simple approaches that can be done to gain some robustness against noisy labels during training. So in this part of the talk, I'm going to talk about one of the early works that we did, and it was presented in NeurIPS 2017. In this part, we're going to target image labeling problem. So the problem is to predict a set of binary labels in an image. We're going to assume that the training data contains some noisy labels. For example, you can imagine that we have used some NLP tools to process text associated with images. So think of like the image on the right as one of the images in the training data, and the caption says something like, "My cat is sleeping in the cooker today." So we're going to process this text to come up with some noisy labels. Here, we're using on the left side the vector y to represent these noisy labels. So because there is words cat and cooker in the annotation, so we know that these entities are present in the image, but because there is no mention of like plant or kitchen or appliance, these classes are missing from our noisy annotation. To represent a clean label, we're going to use the vector t, which is also a binary vector. And we assume that we don't have access to this binary vector during training. So in this part of talk, we're going to assume that we're representing the joint distribution of clean and noisy labels together using a conditional random field. Conditional random field defines the joint property distribution over clean and noisy labels using an energy function. If you're not familiar with conditional random fields, don't worry. We're gonna soon actually try to remove this dependency in our model. But the main reason that we actually initially we're using this is because if we have a conditional random field, we can easily define a conditional property distribution over clean labels t, given x image, represent image, and y noisy labels very easily. The easiest way for training a deep learning model is to use maximum likelihood estimation. So let's say you have given a training data with images and noisy label, and the easiest way of training your model is to maximize the log probability that your model predicts for noisy labels. Y's here. Remember that the way that we define the joint distribution, it involves both a distribution over both clean and noisy labels. So in order to maximize log probability of noisy labels given an image, we need to marginalize out the true labels in our joint from our joint distribution, right? So we need to sum over all the possible configurations of clean labels in our joint distribution in order to get the probability of a noisy label given given the image. So we have in the marginalization step, we have this intractable summation shown in the bottom. Usually we use expectation maximization approach for training such model. So you can think of expectation maximization step as a iterative algorithm that iterates between expectation and maximization step. In the expectation step, what we are doing on the left side, you can see, we are trying to create a distribution that defines the distribution of clean labels given image and noisy labels. And in the maximization step, we use this distribution to infer the clean labels that are missing during training. So we use, you see that expectation is with respect to Q. So we try to, you can think of like we're sampling clean labels using Q, and then we maximize the log probability of the joint over both noisy and clean labels, right? So you can think of like in the expectation step, we are using the model itself to infer the clean labels that are missing. And in the maximization step, we're trying to maximize the log probability of the noisy and clean labels that we just inferred in the previous step, right? So we're using the model itself in the expectations step to infer the clean labels, and then we fit the model to the labels that it has been inferred in the previous step. So if we make mistakes in the expectation step, when we're trying to infer the clean labels, we're kind of fitting our model to the wrong labels that have been inferred by the model itself. So the mistakes will kind of encourage the model to predict the same wrong labels. In order to fix the issues that EM has for training from noisy labels, here we introduce regularized EM. In many applications, we have access to some auxiliary source of information that can help us infer true labels. We're gonna introduce a new distribution called auxiliary distribution that is formed from that auxiliary source of information. For example, in the case of image classification, we can use text data to create a distribution that infers true labels given some noisy annotation. Then we modify the EM objective and we introduce this new optimization in the expectation step of EM. Here we have linear combination of two KL terms. The first KL term measures the distance from the distribution Q to the prediction that the model P makes for true labels given images and noisy labels, and the second KL divergence measures the distance from the same distribution Q to the auxiliary distribution that is formed from the auxiliary source of information we have. In the paper, we showed that this scale minimization has a closed form solution, and the closed form solution can be obtained using the geometric mean of the two distributions shown here. The first distribution is the distribution created using the model itself to infer true labels given image and noisy labels, and the second distribution is the auxiliary distribution that is created from the auxiliary source of information. The interesting thing about the geometric mean of two distributions is that it can be formed using the weighted average of probability distribution in the log probability space. So it can be implemented very easily by just taking the average of logits in classification, for example, before applying softmax. So now if we use regularized EM, we modify the expectation step to have the geometric mean of the distribution introduced by the model, as well as the auxiliary distribution that is given to us through the auxiliary source of information. So we modify the expectation step, but on the right side for the maximization step, we're using the same step. We infer true labels using Q, and then we maximize the joint probability of noisy and clean labels under our model. So you may now ask me, how are we going to set alpha? So we know that during training, initially, our model is not accurate in terms of predicting the distribution over true labels. So we can set alpha to a very large value so that we use the auxiliary source of information or auxiliary distribution to infer the distribution over true classes. And as training goes on, we can reduce this coefficient alpha so that so we can use the model itself to infer a distribution over true labels. Recall that we introduced our framework for training a joint distribution over both clean labels and noisy labels, where the joint was represented using a condition random field. But you may say that you like to use the framework to train a classification model that only predicts the clean labels, not the joint distribution. In our work, we actually observed that we can use this framework for training a classification model that predicts only class labels. In this case, we need to modify expectation step again, and we're going to still use the geometric mean shown on the left side, where the geometric mean is happening between the predictions that are made using the classification model and the distribution that is induced by auxiliary distribution. So we call this a self-correcting inference, where instead of using just noisy labels, we're going to use the model itself in order to infer a distribution over true labels. And the principle is the same. We're using geometric mean between two distributions. In the maximization step shown on the right side, in order to train the parameters of model, we're going to use Q to infer the true labels, and we're going to maximize the predictions, the probability of the predictions that are being made using the model for those inferred true labels. So you can think of this maximization step as a training cross entropy loss, where Q is the soft labels. So the take-home message from this part of talk is that label noise is a common problem in many applications. If you have access to some auxiliary source of information, you can use that to correct some of the noisy labels during training. We came up with this self-correcting principle that uses the geometric mean of two distributions. One is the model itself and the other one is the auxiliary distribution, to come up with some distribution over true labels. So in this part of talk, I will switch gear to object segmentation problem, and I will show how our model can be used for this task. This part of talk was presented originally at CVPR this year, so if you're interested, I would definitely encourage you to check our paper. So we know that this semantic object segmentation is actually a very challenging problem for collecting annotation. Segmenting objects is a very subjective problem. Usually in the boundaries of the objects, we cannot make a decision that which pixels belong to object. Usually, if objects have very small resolution, it's very hard to label them. And also, labeling is very expensive for segmentation tasks. For example, previous study showed that segmenting an object takes 8 times more time than just drawing a bounding box, and it takes 80 times more time just saying that there is a bicycle in this image. So in this part, we're going to have a particular setup. We're going to assume that we have a small, fully labeled set where images are labeled with both bounding boxes and the segmentations. You can see it on the left side. And we're going to assume that we have a large, weakly supervised set where we only have access to bounding boxes. So we're using bounding boxes instead of the object segmentation mask to reduce the annotation cost. But we assume that we have a small set that contains both bounding boxes and object segmentations. Remember that on the weakly supervised set, we don't have access to the object segmentation. So in order to infer object segmentation in this set, what we can do, we can use the fully supervised set F to train a segmentation model. So we're showing the segmentation model here. We're going to come up with a new segmentation model. We call it auxiliary segmentation model that will take image and bounding boxes, and it will try to predict the object segmentation. And we know that we can train this model using the fully supervised set, because on this set we have access to both images, bounding boxes, and segmentation labels. So this is a very simple segmentation model, and we can train it on fully supervised set. Then when it comes to training the main model here in the blue box, the primary segmentation model, we know how to use the fully labeled set, right? We can easily feed the model with our images, and we can use cross-entropy loss to make sure that our model predicts the segmentation map given in the annotation. But for the weakly supervised set in the bottom, we have only bounding boxes of the objects available. So in order to infer their segmentation mask, we can take the images from the set and the bounding boxes, pass them to auxiliary segmentation model that we trained in the previous step to infer a distribution or some soft labeling of object mask given the image and the bounding boxes. So here we represent this output of auxiliary segmentation model using Q in the bottom. And you can think of that we can just technically just use the output of this segmentation model as soft labels for training the model on weakly supervised set, right? So if we do this is actually similar to what we were talking in the previous part. This is kind of like our technique where we're only using the auxiliary source of information as target. So it corresponds to geometric mean, where alpha is infinity, and we only use the auxiliary source of information as our guide during training on top of noisy labeled instances. But from the previous part of the talk, we know that we can now use the self-correction principle in order to improve the predictions that we're making using the auxiliary segmentation model. So now here we show that actually we can use the geometric self-correction from the previous part by taking the geometric mean of the auxiliary distribution as well as the prediction that model makes in order to infer better segmentation mask on the weakly supervised set. So in this part of talk, we showed that collecting annotation for semantic object segmentation problem is very costly. Label noise is unavoidable given the subjectivity of the problem, and we show how semantic object segmentation problem can benefit from robust training models that we discussed in this talk. In the third part of the talk, I would like to switch gears to object detection, and I want to show how we can use training from noisy labels in order to gain robustness against domain shift. So this part of the talk is based on the work that we did at ECCV 2019. So many of you know that domain shift is actually a common problem in computer vision problems, because we usually train our models in a data set, and when we deploy it in real-world applications, the data that is coming to our model is coming from a slightly different distribution that generates data. So here we want to see if we can formulate domain adaptation problem for object detection problem using training from noisy labels. So we're going to assume in this part of talk, in the bottom part, that we have a source domain with object bounding boxes annotated in this domain, and we're going to assume that we can train a model, an object detection model such as FastRSNN on the source domain, and we can apply it to a target domain to get some noisy labeled bounding boxes. So we're going to assume that we don't have any labels in the target domain. We only use the detector itself trained on the source domain to get some noisy labeled object bounding boxes in the target domain. So if we want to use these noisy labeled object bounding boxes in the target domain for training, we need to come up with a robust training framework for object detection, which is the goal of this part of stuff. So again, in the phase one, we train a model on source domain, and we apply the target domain to get some noisy object bounding boxes shown on the top from the target domain. In the second phase, we're going to train an image classifier using the object bounding boxes detected in the first phase. So we're going to feed all the bounding boxes that are extracted from both source and target domain to an image classifier, and we're going to train it. We're going to call this image classifier using p image, And this classifier can be thought as a prediction model that will give a classification score to each bounding box. And we will use this as auxiliary source of information in the next phase. Given this auxiliary source of information or auxiliary distribution, we use that to train a faster RCNN that is robust against label noise. So we can use our framework to apply some robustness against noise. Let's see how we can make faster RCNN robust against label noise. Recall the faster RCNN has two heads. In one head, it tries to predict a class in the bounding box, and in the second head, tries to refine the bounding box around the originally predicted detection. So first head can be thought as a categorical distribution that predicts the presence of a particular class, and the second head can be thought as a normal distribution that defines a location for the bounding box. In this work, we introduce a classification error correction using geometric mean principle that we saw earlier. We're going to take the geometric mean of the image classification that we get from the second phase, as well as the classification score that we're getting from faster RCNN, in order to infer a distribution over true classification properties in each bounding box. We also came up with a new mechanism for bounding box refinement in order to correct the location of the detected bounding boxes around a particular bounding box using faster RCNN itself. So here again, we're using geometric mean of two normal distributions instead of the categorical distribution we were using, and we show in this paper that geometric mean of normal distribution itself is another normal distribution. The take-home message I'd like you to have is that semi-supervised domain adaptation can be also modeled as training from noisy labels. In fact, recently, some work showed that you can use this principle in order to even train better image classification models that can obtain state-of-the-art results on ImageNet classification problem. We applied these techniques, in fact, before recent methods on problems like segmentation as well as object detection, as you saw. In object detection, the auxiliary distribution can be constructed using image classifier. So that way we can actually encode cues that we don't have in our object detection model. And also, we showed that actually self-correction principle can be applied not only to categorical distributions, but also for normally distributed object localization models. So it can be done basically for any forms of distribution that we have in the prediction part. In this part of talk, I will talk about contrastive learning and how we can use this framework for training phrase grounding models in a weakly supervised setting. This part of talk is based on our ECCV 2020 paper that will be presented at the main conference this week. So if you're interested in this area, I highly encourage you to check Tammei's talk this week. So as you know, text and images are abundant on the web. In fact, early work on training from noisy labels were advertised as webly supervised vision models. However, recently there has been a tremendous progress in unsupervised representation learning for natural languages. For example, BERT and GPT-3 and many other recent language models have shown very encouraging results in learning representation for words in a natural language. On the other side, in computer vision, contrastive learning is showing a promising performance for representation learning. So in this part of talk, we'd like to answer whether we can use contrastive learning for training deep vision models from image captions as noisy annotations. In this part, we're interested in weakly supervised phrase grounding. In this problem, we're given a set of images and captions describing those images. Our goal is to predict the location in the image for each noun phrase. But however, since our training is weakly supervised, during training, we don't have access to the location of noun phrases on the image. We're only given a set of images and captions. Our grounding model consists of a pre-trained object detector that extracts region proposals and image features in those regions, a language model that extracts contextualized word representation for every word in the caption, and a learnable attention mechanism that assigns regions to words. For learning, our key observation is that estimating the mutual information between a set of image regions and caption words requires alignment between them. However, since estimating mutual information is intractable, instead we maximize info and C lower bound with respect to parameters of the region word attention model. and we show that at the end of training, attention model can learn grounding. Contrastive learning using influence involves learning a compatibility function between a set of region features R and contextualized word representation W. Influence objective encourages the attention model to have higher compatibility scores for true word region pairs compared to incorrect pairs. Images with corresponding captions serve as positives, and negative pairs could be constructed by pairing the original caption with randomly sampled images as shown on the left side. We can also construct negative pairs by pairing the original image with a randomly sampled caption. We designed the compatibility function such that achieving a higher compatibility score corresponds to correctly assigning regions to words. For negative pairs, we expect the words not to select any region strongly, which corresponds to producing near uniform attention over regions. While it's common to construct negative pairs by replacing either the image or caption in a true pair by a random sample from the training data, we propose to use the language model to extract plausible negative captions. For example, on the right side, you can see that the word donut in the true caption is replaced by the word cookie to create a negative caption. We will take a closer look at this in a moment, but first let us look at the compatibility function. For computing the compatibility score, we start with an object detector to extract a set of regions and representation describing those regions. For the language part, we use a language model like BERT to extract a contextual representation for every noun phrase in the caption. We then use a fully connected network to extract keys and values for every image region, and queries and values for every word representation. Then we use the queries and keys to calculate attention for each word over all the regions. Then we use these attention scores to aggregate the values that are extracted over the image regions. This is called attended visual representation that is extracted over all the regions. Then we use the dot product of this vector with the value vector extracted for the word in order to calculate the compatibility score. In this work, we also show that we can use a pre-trained language model to extract hard negative captions effectively. Given a positive caption shown here, we use a pre-trained language model like BERT to generate contextually plausible words that can semantically complete the sentence. Let's see how our phrase grounding model works in practice. Here we're examining our model on the Flickr 30K entity test dataset. Here we're comparing using a BERT initialized randomly versus a pre-trained model. As you can see, we get around 10% improvement in accuracy by using a pre-trained BERT representation extracted on the words. If we use randomly sampled negative captions, we almost don't see any significant improvement using randomly generated captions. However, if we use our contextually plausible negative captions, we see around 10% improvement introduced because of using hard negatives extracted with this approach. In this part of talk, we saw that the recent advances in natural language processing have brought us very rich representation of words and sentences that can be used very easily for vision tasks. We also showed that contrastive learning can discover object locations when maximizing a lower bound on mutual information between image region features and pre-trained word representation. We also showed that language models like BERT can help us extract plausible negative word substitutes. If you're interested in this work, I encourage you to check the project website listed below. In this talk, we saw that label noise is a common problem in many real-world applications. We also saw that self-correction mechanism can be used to gain some robustness against label noise during training. Even though this area of research is very important, unfortunately there has been very little progress to tackle label noise during training deep models. We also observed that contrastive learning is an effective framework for learning from text data in a weakly supervised setting. Also, we saw that recent language models contain rich representation that can be used for training vision models. I expect to see more work in this area in the near future. In terms of theory, there is unfortunately a big gap between theory and practice currently. Many theoretical guarantees make assumptions on the model that doesn't apply to the real-world problems. As a community, we need to work on building theoretical understanding of how to gain robustness against label noise during training of deep learning models for real-world applications. Thank you very much for attending this talk. Please feel free to connect with me through ECCV's platform during the conference. You can always reach out to me through email or Twitter as shown on this slide.